Hello everyone, welcome in this new recording, as usual. Today I would like to talk about the origin of the Canvas library, which I've been working on for quite a few months now. In the latest video, I actually demonstrated quickly the new blueprint display that I have for the Nerv Lab project. And in fact, this blueprint display is completely based on the Canvas subsystem. So I've just prepared a small, well, page of notes like that for this recording. And before we really go into the core of the video, which is really the rendering process itself in the canvas, there would be a lot to mention and to discuss on the canvas class because it's a pretty complex class. In fact, I can show you that already. The header file is pretty long. There are a lot of functions and yeah, a lot that could be discussed here, but we're going to try to keep it simple for this time, and we're just going to be focusing on the rendering, the core of the rendering itself, which I find very interesting, and it's a processing that was a bit well, unusual to me. So yeah, let's focus on that. But before we go in that, some context details maybe. The Canvas class was really constructed using this Nano VG library as a reference. So that's why I have the page here. This library is basically providing you with a framework to render any kind of shape, actually 2D shape, using some kind of SVG path description for all your shapes. And in fact, this one is just a minor update from the base one, which is the Nano VG library. Okay, I already have the page in fact here. So this is where you have the most important base stuff for this rendering system. Point is, this library is implemented using the OpenGL API, so that's not really what I wanted myself, because I really wanted to build everything in WebGPU, and there was no existing port of the library, I think, at least. But anyway, I decided just to go from scratches, taking this as a reference and implementing everything from the beginning in WebGPU. Okay, and in fact, this picture here is an example of what you can generate using the Nano VG library, and we'll get back to this because I have actually implemented on my side this window display here, and also the color wheel that we have here. So yeah, we'll mention that again later. Now, I started working on a very simple test, of course, so just trying to display a rectangle, a circle, applying different texturing effect, because I guess you can't really see that clearly here, but you have support for gradients effect in the coloring, and yeah, you maybe see that a little bit here because it's white at the top and there's a darker color at the bottom, so you have a linear gradient, radial gradient support, well, all this kind of stuff for the paint of your shape. So this part I had to investigate quite a lot at the beginning, but then I actually moved to a simple widget display. So this was the initial version of it. This is a small recording that I made some time ago, though the first version here was only displaying a few rectangular sub-widget in a big gray widget, and also I eventually added support for the text display. And when this was done, I moved to this one, this implementation of a more complex widget, which, as you can see, is basically reflecting what you have in the example image here, with maybe a few small changes. And then this is the version where I have the color wheel completed. And in fact, the interesting thing is everything I was building myself here, including the complete widget here, was done with a dedicated windowing framework that I am implementing at the same time, and which is basically similar to the Qt library. Here is, for example, the class which I'm using to build this widget and stuff window. And if you're familiar with Qt, you should notice that there are some elements that are very similar to what you can find in Qt. For instance, you have this notion of layout. So you have a vertical box layout, a horizontal box layout. Then you have a combo box here, a label class to display a simple text, line edit. All these are classes that I built from scratches and which are basically simulating the behavior that you could get from a Qt. Okay, and when I was done playing with this color wheel implementation, this is when I decided to move to concrete implementation of those blueprint nodes that we have in the current version of the Nerv Lab project. So yeah, this is also still pretty much work in progress. There would still be a lot to add in the Canvas class to support all the features that we have in the NanoVG library, but for the moment what I have is basically all I need to get this working properly. So I'm not really in a hurry to add more stuff, but I could do that later on if I really need to. Anyway, let's now move to the basic idea that you have in the Canvas library. I mean, in the Canvas class. So you really want to use this class to display any kind of shape. That could be a simple rectangular shape, or a star, or a circle, or even some kind of composed shape like what I wanted to display here, which is you're displaying a rectangular, a rectangular element, but with a hole in the middle, and that could be a circular hole, and that would be empty, so there would be nothing displayed in this part. You could use that for more complex display. In this case, for instance, you could have this rectangular shape, and you could remove the corner with free circle that could be removed from the shape itself. And here I would be removing a small square area, so that would be discarding this part which was painted in red and only displaying a shape like this one, if you want. Okay, so I guess you get the idea. This can also be used to draw simple lines, for instance, or any kind of complex shape in the end. All those shapes, they are going to be constructed with a class which I call Path2D. And here is actually this class. It's actually one point where I'm drifting a little bit away from the original implementation that we have in NanoVG, because in NanoVG you would be constructing your path directly with the NanoVG context. So I decided to add a dedicated class on my side, and you have all those functions which are the common and standard function that you could find, for instance, in SVG path generations. That would be to move your cursor location to a point starting from the current position. I mean, move, no, that would be just not drawing anything anyway, it's just going to move you there. Then you have the line, which is going to draw a line from your current position to another location that you're specifying here. You have absolute or relative version of those functions. You can draw curves, you can draw quadratic Bezier curves. This is an arc segment or something like that. You can close a path, and then you can do more advanced operation like inverting a path, manually adding some segments, or transforming this path somehow with a transformation, a 2D transformation, of course. And you have other static function to draw simple shapes more directly. Alright, so yeah, probably not needed to go into more details for this class for the moment. And yeah, next, the other important concept that we need to mention is that all the shapes that we are creating as 2D paths, you can either then draw them as field object. So in this case, if you have a square or rectangular object like that, filling would be painting all this. Or you could use a stroke operation, and if you do stroke instead, it means that you only want to display the edge of the shape itself with the color that you're specifying and so on. So you're not feeling the content. I'm drawing like a baby, I guess. Anyway, the important thing here is that stroke is not really happening at any point, because what is really happening under the hood is that a stroke is in fact converted into a fill, because if you start with this list of segments, or this path if you want, in black, you are going to generate the segment in red. So this one will be the outer rectangular shape, and this would be the inner rectangular shape. So it's going to be removed from the outer one, so that part is going to be empty. And this part here is the one that will be painted with the provided color. So in the end, it looks like you are stroking something, but it's not really that. You're actually just feeling all the time. So now let's get to the actual rendering principle itself, which I think is the interesting part here. And the point is, all the shapes that you are defining here with this canvas class, you are going to render them without any kind of polygon generation at all. So that is a funny thing from my perspective, and we're going to try to explain that. Let's say, for instance, that you have this shape. Then the thing is, you are going to describe this shape as a list of segment. Sorry. So you're going to start from point 0, go to point 1 with one segment, then point 1 to point 2 with another segment, then 2 to 3, then 3 to 4, and then 4 to 0 to come back. So you have 1, 2, 3, 4, 5 segments here. And what you do, in fact, is, given this shape, you need to define an encapsulating rectangular area, which could be technically whatever you want, but in fact, in my implementation, I'm just using the bounding box for the shapes. This is working just as well. So in this case, that would be the box just like this. Yeah, I hope you don't mind the drawing. Okay, once you have this encapsulating box, you only need to consider all the segments one by one, in fact, and you can do that separately or in parallel, so that's a great thing here. So if you just consider this first segment here, you also need to keep in mind that the segments have to be oriented. So if your segment is going from the left to the right, then the orientation is, say, positive. And then you consider this trapezoid shape under your segment going to the bottom of your bounding area, and all the point that you have in this trapezoid shape should be assigned a coverage value of 1 when they are inside this area, and everything else is considered to start with a coverage value of 0 if you want. Next, you can do that for the next segment, so that would be the segment just here. Again, you're going from left to right, so all the point inside the trapezoid shape should get a value of 1. So it's also valid for the points that you have here, so all of them will get a value of +1. But then you continue with the third segment, and this one is going backward because the starting point is on the right side and the ending point is on the left side of the start. So it means that your trapezoid shape is considered to be inverted, and in this case you still consider the trapezoid shape, but all the points that are inside are given the coverage value of -1 instead. So you get -1 here, you get -1 for this shape here also, and also -1 here. And then the idea is simply that you have to sum the coverage that you get for all your points on, all the points that you have in your bounding box here, and you sum all the values that you have calculated for all the segments. So if you are, for instance, on one point here, you have this segment which is going to give it a value of +1. This segment is not going to change anything, so means that for this segment the value here would be just 0 basically. This one is not going to change it either, this one won't change anything, and this one will not. So the end value will just be +1. But now if you consider a point which is here, for instance, the first segment will give you a value of +1. This one will not change anything, this one will not either, nor this one. But this segment here is basically the computation done here, and your point in this case, which would be somewhere here, will get another value of -1. So if you sum all those values together, you get +1 plus -1, which give you a final coverage of 0. So this is one I have depicted here, because if you do that for all the points on your box, the end result that you get is that all the points that are outside of your shape will get a coverage of 0, while all the points that are inside will get a coverage of +1. And in fact, this is basically all you need to draw the shape, because this coverage is something that you can consider to be the alpha value of your pixel, for instance. So you can use that to decide what is the visible part of your shape and what is outside and invisible. And yeah, that's all you need, and you can draw your shape then without any kind of polygon computation, which is really cool, I think. I mean, it's probably a bit expensive, but it's cool anyway. Now, just maybe an additional level of detail on that is, if you want to consider what's happening exactly, I mean more precisely at least, on a pixel level when you're doing the computation in the canvas. You could imagine, for instance, that the canvas is going to render the output on a texture which is a 8x8 texture. So that's something I try to display here with this grid display. And all those small squares here are the pixels that have to be rendered. So you would start, for instance, with your shape to be rendered, and you would need to figure out what are all the encapsulating pixels that you need to consider for this shape. So that would give you this red box here. And next, all you need to do is simply to perform the same kind of logic of what we have described just above. So you will start with your first segment here and consider a trapezoid shape underneath and perform the computation of the coverage for all the pixels that are, well, touched by that trapezoid shape. So this one is not touched, so not affected at all. This one, there's a small bit that will be touched. So you compute the coverage and it's going to be a very small value, like 0.05 or maybe even less than that. So a very small value here. Then you get for this one a slightly bigger value because this part of the pixel is covered. Then for the pixel underneath here, you could imagine maybe that the coverage would be 0.5 because we're covering half of the pixel with the trapezoid shape. Again, 0.5 here, 0.5 here. This one would be a coverage of 1, and here you could say maybe 0.75, so 3/4, and same here, 0.75, say 0.4. Here you could have maybe 0.8 or something like that. So yeah, you get the idea. We have a first coverage value computed for every of those pixel for the first segment, and then you just do the same thing for the next segment here. And what's happening is here is, if you consider this pixel, for instance, let's get back to the color like this. So this pixel on the first segment, we got a coverage of 0.5, and then with the computation done for that segment, we'll also get another value of 0.5. And what you're going to do, as I told you, is to accumulate this value for the pixel. So now it's going to give you a coverage of 1 already. And yeah, you just keep going. That's going to give you a coverage of 1 here also. Here it's going to give you a coverage of 0.5. But if you reach this segment at the end, then when you do the computation again for this pixel, it's going to remove a little bit. So the final coverage for the pixel would be 0.6 or something like that. Again, then if you continue with this segment, you do the computation for this pixel, and it's going to give you minus 0.75. So it's canceling the computation done for the first segment, and then of course you get the coverage of 0 for that pixel. So yeah, it's working exactly as we mentioned above, and even more precisely than what you would get with a simple polygon display, because what you get in fact here is really anti-aliasing out of the box, because you get partial coverage for those pixels that are at the very border of your shape. Now, the final point I would like to mention is that in fact all this coverage computation is done in a compute shader on our side in WebGPU. And the other very cool upgrade done compared to the NanoVG library is that we can now, in fact on our side, process all the shapes that we want in a single compute pass. To do that, what you really need to do is to allocate this coverage area here per shape. So you could have a dedicated coverage area for every single shape, and then you build a large coverage buffer, and you can then process all the segments for all your shape in parallel. So you could put all those segments in a big buffer. That's what I do myself actually. So if you have those 4 shapes that you want to display, you have the number of the segments that is incrementing, and they're all stored one next to another in a big buffer. But the thing is, you also need some information concerning the shape itself, like what is the bounding box for the shape, what is the transformation, or other stuff. So you need a mapping of the segment to the corresponding shape. So you also need another buffer which would contain something like that. For the first 5 segment here, the shape index would be 0, indicating that all those segments are for the first shape. Then the next 5 segment will use ID 1, so for the shape 1, and so on. And of course, you also need then another buffer where you're also storing the actual shape parameters. So in my case, I have another class which is a canvas layer, because I also support multiple layers when in the canvas subsystem. And this is where I have this render parameter description, which is in fact the shape parameter that I'm thinking about here. And what we have here, for instance, is we have a dedicated scissor matrix, paint matrix, transformation matrix, the inner color, outer color, the texture rectangle in case we're applying a texture on this shape, the bound, so the rectangular bounding box, and other settings like the render mode, the patch index. Okay, patch index is in fact, the coverage patch index that is supposed to be used for this shape, because there is another layer of complexity on top of that, which is that I'm also able to share the computation of the coverage for multiple shapes that are going to be displayed at different places on the screen. Let's just not go into much details maybe. And well, this is it. With this kind of setup, then you can compute the coverage for all your shape in one pass, one compute pass, and then you just need a second pass where you're actually going to use this coverage information to actually paint the details for your shape on screen. So you use this coverage as an alpha mask basically, and then you use the other information that you have for your shape, like what is the color, what is a gradient that you want, effect that you want to apply, what is the image that you want to sample, and use that to paint your final display. And so yep, I think this is all I wanted to mention on this one. Again, I tried not to go into too much details, even if this is already pretty complex, I think. But there would be a lot more stuff to mention on the canvas, but I'd probably keep that for separated videos, or maybe just not do anything concerning that at all. Anyway, if you have any question concerning this topic, just let me know in the comments as usual, and otherwise I'll see you next time for another video like this one. Bye bye, have a nice day, see you.